In this video, we'll compute the Laplace transform of a couple of examples of simple functions and also talk about the fact that the Laplace transform is linear. Recall our definition: the Laplace transform of a function f of t, some function which is defined for non-negative values of t, is the improper integral from 0 to infinity. We take our function f of t and then we mix it in with this exponential factor e to the minus st dt. The s is some parameter which we haven't specified, but you should treat it as a constant as we do the integration. For our first example, let's take f of t to be a constant function. In fact, let's take it to be 1 for all t greater than or equal to 0. I'd like to find the Laplace transform of 1. How do we deal with constants? So we go to the definition and I integrate from 0 to infinity, and all I do is just take the function I'm working with, f of t, and I replace that with 1 here, and I still have the exponential factor as just part of the definition. By definition of an improper integral, it's a limit of a definite integral, so I'm going to have some parameter b. That will go to infinity, and I'll integrate from 0 to b e to the minus st. I really didn't need to write this factor of 1, so I just dropped it. So we're going to take a limit, we're going to find an antiderivative for e to the minus st and then evaluate it between 0 and b. I integrate the exponential, it's going to be e to the minus st, and then we've got to divide by that minus s, whatever that parameter is, to account for the chain rule. If you take the derivative with respect to t of this, you get e to the minus st. Right there, I guess we're assuming that s could not be equal to 0, or this expression wouldn't be defined, so somehow that affects the domain of this Laplace transform. Next thing I need to do is apply the fundamental theorem by evaluating my antiderivative at b, and I'll put that expression in there, and then I'll evaluate it at 0 and put that expression in there. Remember, the variable of integration was t, and so we're going to evaluate t at b, and then we're going to evaluate t at t equal to 0, so we'll have e to the 0 over minus s. Observe that if I have a positive value of s, that because of the built-in minus sign in the exponential, this will decay as as b gets large. So e to the minus sb will go to 0 as b goes to infinity. That means this term will go away, provided s is greater than 0, and then this term will just be 1 over minus s. So we'll have 0 minus 1 over s, and simplifying we'll have plus 1 over s. So in conclusion, the Laplace transform of 1 is 1 over s, and that converges, that integral converges provided my value of s is greater than 0. Okay, let's look at another example. I'm going to take the Laplace transform of an exponential function, so something like e to the t, but I'm going to allow some parameter to be in there as is typical. I mean, we don't want to be too specific, so I'm going to let a be some constant, so something like e to the 2t or e to the minus 5t. These kind of functions we want to find their Laplace transform. The Laplace transform of that then we'll be just replacing f of t in the definition with e to the at. And we include this exponential as well, e to the minus st, as part of the definition. These are both powers of e, so the natural thing to do is to multiply them together by adding their exponents. And so I'm going to have e to the at minus st dt. And the right way to think about that is it's e to the t with some parameter in front, and that parameter is a minus s. So I've factored out the t in the exponent, and I have a minus s times t. Okay, that's a limit of a definite integral. So I'm going to introduce a parameter b, let b go to infinity, and then we'll do our integral. We need an antiderivative for that. I'll put that in the brackets here, and we need to evaluate that between 0 and b. integrating this expression here, it's just like when we integrated the e to the minus st, it's just that the parameter now has changed, it's a minus s. So I'm going to get that exponential, but I need to divide by a minus s. And we need to plug in a lot of symbols floating around. The variable of integration was t, so I need to plug in t equal to b and t equal to 0. And we'll put those into the brackets. T equal to b, I'll get e to the a minus s times b now. And then when I plug in 0 here, I'll get e to the 0, I'll have 1 over a minus s up top. Come to the moment where you have to do a little bit of analysis and think about what happens as b goes to infinity. You want this term to decay to 0 for the integral to converge. So you want a minus s to be a negative number. You want a minus s to be less than 0. If that's the case, the exponential will decay to 0 as b goes to infinity. And therefore our limit will be 0 in the first term, and then minus 1 over a minus s, so minus 1 over a minus s. And distributing that minus sign through to the denominator, I'm just going to swap the order. That's the same thing as positive 1 over s minus a. So our conclusion is the Laplace transform of e to the at is 1 over s minus a. I needed this condition to be true. A minus s should be less than 0. That's the same thing as saying that s is bigger than a.